Okay, so finally we will try to start today's lecture. And so last time we closed the topic. Sorry, just a second. Okay, so last time we basically closed the chapter regarding the kinematics of rigid bodies. Basically, we were able to, the aim of that section was to be able to describe the position and the orientation of a rigid body in the 3D space. We introduced the concept of inertial and local frame, and we also were able eventually to parameterize the orientation of a body, of a rigid body in space. We were able to deal with a series of successive rotations, and eventually we derived the expression of the velocity and the acceleration of a system of bodies in space. All these aspects will in fact be used, so they will come back again in what we will commence today, that's to say the treatment of the dynamics of rigid bodies, whose final goal is to basically derive the equations of motion of rigid bodies, okay? So we will deal with no more just motion of bodies, but we will deal with forces and constraints and so on. So we start today the chapter about dealing with the dynamics of rigid bodies. In particular, we will start this treatment introducing the concept of generalized coordinates. What are generalized coordinates? Well, if you remember, the position of the body I within the space was basically represented like this eventually in the last part of our section. So position Pi of a point over the body number I was equal to R, which is the position vector of the origin of the frame I, plus the rotation matrix I applied over a vector defined in the local frame for the body I. So how many dependent parameters are here defined in order to be able to define, sorry again, the repetition, the position of the point? So we have 3 components, right? R1, R2, R3 of the vector R. This is for the position. And then we have, depending on the parameterization, we can have either 3 or 4 parameters. Okay. So we can have basically, for example, we can have 0, theta 1, theta 2, and theta 3. If we are dealing with, for example, Euler's parameters. On the other hand, we could have, for example, phi, c, and theta. We are using Euler's angles. Okay. So these are 3 parameters for position. Basically, the local frame, and then we have 3/4 parameters for orientation, right? Okay, always of the body. So this basically ends up saying that we have either 6 or 7 parameters. Why are they called generalized coordinates? Because eventually these parameters, which are also called coordinates, as I was mentioning, they do have general natures, right? We can have displacement, so this can be a length, okay? This can be a rotation. Some of them actually are the composed, so these are angles, for example, in the case of US angles. In the case of US parameters, some of them are the component of the axis of rotation multiplied the cosinus of an angle and so on. So they have different physical meaning and physical dimensions. So that's why they are called generalized, okay? Because we are not talking about lengths. We are not in general talking about angles. We can have, for example, velocities, not right now, but this can be an option, as we will see later on. So the physical nature, the physical meaning of these coordinates, which are used to define the status, okay, of a body, of a system, can be different, can be various. So that's why from this we have the definition of general coordinates. In fact, generalized coordinates in more appropriate way. So we have 7 or 6 parameters to define T. Okay. Okay. This can be, in fact, seen eventually if we make an example. Actually, more than that, just to close this aspect, typically the general coordinates are grouped, okay, in a vector, and the most popular notation to define the general coordinates is makes use of the letter Q. So our generalized parameters, vector of generalized in our case is Q, okay, letter Q, with Q being equal to what? Well, R1, R2, R3, and for example, I don't know, can I have in case of US parameters are adopted, general parameters. Now, let's look at this picture now. Okay, so if you look at this, so you see you have a system of bodies. In general, in this case, we have this code, but for a system, because we will always deal with typically with a system of bodies. Okay, for a system of, let's say, MB bodies, we're always talking about rigid bodies. Okay, so rigid bodies. We have how many parameters in 3D space? So for one, we have 6 or 7. Okay. For NB, we're going to have 6 or 7 times NB, right? So 6 or 7 times NB parameters. Okay. So our Q typically will be composed of what? Of Q for the body one transposed here, 2 transposed, okay, 3 transposed, so on until we arrive to MB transposed, all of which is transposed. Okay, and this is a vector of, in this case is 1, let's say 6/7 times NB times 1. Okay, so this is a column vector. All the generalized parameters describing the states of all the bodies, and so eventually the state of the system in its completeness. But as you are actually seeing this picture, there may be, you know, that some of these bodies are typically connected. Between them, they can be connected to the ground. Okay, so whenever you have to implement, whenever you have to describe interdependence between the bodies or the bodies and the ground, you need to insert a constraint, okay, within your system. So a constraint is a dependence between bodies or a body and the environment, let's say. Okay. What? Because this is a column vector. Transpose is a row vector. So these are all row vectors. This has to be a column vector. So that's what the transpose eventually. Okay. That's by definition. Typically, we are always talking about, so in our formalism, forces, position vectors, all this sort of vectors we deal with description of the status of a body always comes in column. But that's not actually our formalism. This is typically as it is done also in every other courses in this in other courses as well. Okay, so typically position vectors, velocities, forces are all column vectors. Okay, these are typically treated like this. Nothing, you know, forbids that you can do also treat them like rows, but this is not just typically a choice. You know, you can actually have a dual formulation in which everything is treated as rows. Yeah, you can do that. So what do they do when they enforce this dependence between bodies or between a body and the environment? They basically come in the form of equations, okay? And this equation, they do involve what? Some, possibly all, the parameters, okay? So these equations are enforced in terms of the generalized parameters, okay? So constraint is a very important aspect. Come in the form of equations. In the QIs. Okay. Okay. So there are basically some equations that, again, eventually, we will see some examples today, that enforce relationships between bodies. And since the bodies are described in terms of generalized coordinates, these constraints are typically enforced in terms of generalized coordinates. This adds one aspect. This adds one aspect to the definition of coordinates, because if you actually can explain, you can describe some of them in terms of others, you will eventually be able to discriminate between dependent and independent generalized coordinates. Right? So as soon as you introduce a constraint in the model, you introduce the possibility to do a partition of the generalized coordinates between dependent and independent. Okay? Because the constraints actually are a way to link these coordinates so that you can express some eventually in terms of the others. Okay. This is a very important aspect. Soon enforce constraints equations, you introduce independent, dependent coordinates. These are what constraints are for, okay? So that the variation of sum is actually constrained to follow certain rules, okay, that you define through the equations themselves. Let's make an example for that. There's a very mechanism, the Poisselier mechanism here. Have you ever seen them? Something like this. Oops. This is the Poisselier mechanism. Okay. So it's Poisselier, so it's Poisselier mechanism. It's actually quite popular in the aerospace field, but it's a very old concept. Huh? So how many bodies do you have? MB, number of bodies. Please note that, so in order for you to understand how it does work. So this is a mechanism that is meant to convert rotational motion, which is typically exerted here, right, into a linear motion. This eventually can do this or this. Okay, so it's a conversion. Mechanisms are typically done for this, to convert motion. So we have several bodies which are linked through hinges. Okay. Here, for example, you have a body which we can, for example, call like this. So here you have one body, which is this rectangle here, schematically represented. Then you have another body here, which is this this rod. Then you have another here, 3, 4. Then you have another small, let's say, rod here, which is this kind of square here. Then you have 7, 6, 7, 8, 9, and please that these are, as I said, hinges. Okay. So the body count was already done. is equal to 9. So how many Q's do we have? What's the number of general coordinates, which we can define as n, okay? N is equal to 9 times how many degrees of, okay, that's another thing that we will discuss later. How many possible parameters are needed? A 2D case, describe one body like this. We have one rotation and two positions, right? So 3. This eventually will amount to 27 possible parameters. Now, let's count down the number of constraints, number of independent equations. That's another thing that characterize this mechanism. Well, let's start here at point D. So that's a hinge as well. How many constraints do you need to enforce a hinge? Scalar, scalar equation. I would say 2, no? Why? Because when you enforce this rotation, what do you have to say? That the point D belonging to the body 2 and the point at position D belonging to point 1, they must coincide, right? So it means that the vertical and the horizontal position must be the same. So it's 2 scalar equations, correct? So in this hinge D, we have 2 constraints, because you have to say that the position of these 2 points, X and Y, vertical and horizontal, must be the same. So that's why. The parameter which is left is the rotation, which is free. Okay, so that's why. Okay, so this is 2, but then pay attention because this is important. Let's look at the same concept at point C. In point C, you still have a hinge, but you have 3 bodies hinged at the same point. So if you consider the equations in pairs, okay, with the bodies in pairs, so body 2 and body 3, body 4 and body 2, and then body 3 and body 4. For each pair of bodies, you can write down a couple of these scalar equations, okay, right? Because you have to say that point C, the part of the body 2, 3, and 4, which is positioned at point C, must coincide, okay, between them. So 2 equations between 2 and 3, 2 equations between 2 and 4, 2 equations between 3 and 4. So this would appear to count as a 6 constraint. In fact, it's 6. But how many of them are independent? If I say that point 3 and point 4 must be hinged at C, and point 3 and point 2 must be hinged at C, is it really necessary that I add the third couple, saying that 2 and 4 as well must be hinged at 2? No, right? Is this clear? So it means that out of these 6 constraints, which in principle I should enforce, actually only 4 of them are independent, because the other 2 just follow, okay, can be rewritten in terms of the previous 4. Okay? So this means that here, we wrote it, here I have 2 in terms of counts of constraints. Here I have 4, right? And please note that this is a super important concept, the one which we have just intuitively, hinted at right now. The concept of linearly independent constraint means that when I have 2 constraints, I cannot, or more, I cannot write one in terms of a linear combination of the others. Okay, so they are independent. You're actually enforcing a new constraint. When I say that 2 and, for example, 2 and 3 must be hinged at C, and then I say that 2 and 4 must be hinged at C, the fact that I enforce also that 4 and 3 must be hinged at C is not necessary. It's not adding any information, any additional constraint on the system. All right. So same here, same here. Then here we have how many? 4. You see, because they are always 3 bodies connected. And here we have 2. Sorry. But then again, the body 1, for example, is also fixed, is clamped to the ground, right? So you have 3 more. And the body 5 is fixed to the ground as well, so you have 3 more. So let's make the count. And we have 1, 2, 3, 4, 4, so it's 16, plus 2 simple hinges, okay, which amounts to, and then we have 2 fixed constraints. Okay, it's 3 plus 3, so it's 6. So it's 26 constraints. Huh? So how many parameters are left independent? Only 1. Okay. Does this make sense to you? Is actually this that you expected? The answer is yes. Why? Because as I was saying, this is a way, this mechanism is a way to convert a rotational motion to linear motion. So eventually, what you will expect when you see this mechanism working is that point P goes up and down as the body 2 rotates, okay, around point D. So what is eventually the parameters that you need to describe such linear motion of the point P? It's just 1, right? It's the vertical position. And that's why you actually have that this, the number of independent, okay, is actually equal to 27, which is the total possible number of parameters that I ideally need to describe the system, minus 26, 1. This count here is called Grubler's count. And this that you get here, the number of independent parameters possessed by a system, is called degree of freedom. Okay. Also called as DOF, or DOS, okay, abbreviated, degrees of freedom. Please just pay attention to one thing. You see here typically also in the formulation here in the notes, we always denote something or a number of parameters as independent with the subscript I, which is not the superscript I. Okay, so the superscript I is typically used to count the number of bodies. Okay, it's typically referred to the number of bodies. So, for example, when I say E3I, okay, this is the third vector of the local frame for the body I. Okay, while here typically I don't write independent. I write MI. This means independent, but it's a subscript, not a superscript. Okay. Okay. You see here, and the number of constraints NC, basically, of course, must equal to the number of what? Of dependent parameters. Okay? So this is right. So 20 constraints independent. The number of independent constraints equals the number of dependent parameters. Okay? Here is the number of dependent queues. Okay? Which is also typically called as ND. Okay? Well, here we wrote NE. Of course, it must hold that N must be equal to Ni plus Nd. Okay? And this is the partition I was talking about. You see, you can do a partition between of the number of coordinates that you need to describe your system between an independent and dependent ones. Okay? The partition of the queues. Let's make an example and then we will continue next time. Actually, before that, let me just do a classification. So, depending on this one here, the Ni you can classify this is actually typically done for a structure, but also for a mechanism. Okay. Yes. So if Ni is equal to 0, you know how you can call this? Number of constraints is equal to the number of parameters, basically. So that no one is actually independent. You cannot set one as you wish. In Castro, is actually a kind of constraint. It's not really a classification. This is called isostatic. Isostatic. This is typically what you want for a structure, not for a mechanism. Okay, because for a structure you want it to be fit, to be stable in a general sense. Not for a mechanism, because if it's isostatic, a mechanism means that it's stuck, right? Cannot move. Please think of the mechanism that we have just described, the possible mechanism. If this was equal to 0 instead of 1, the mechanism wouldn't move at all, right? Then, if Ni is actually larger than 0, you have something which is unstable, or labile in italiano. Okay? For Ni lower than 0, so negative, allora, you can call it unstable. I think labile is actually also an English term. Otherwise, you can call it stable. Okay. This is actually enforce more constraint that you could. And this actually can happen, right? So last, and then we're done for today. We have another kind of classification, okay, for the constraint, because not all the constraints are the same. Apart from linearly dependent or independent, you can actually enforce another classification between holonomic and non-holonomic, okay? Versus non-holonomic, or also called anholonomic. In Italian is holonomo, non-holonomo, or anholonomo. Okay. So what's the difference between them? We will see them next time into detail. We will go into details. But basically, for holonomic ones, it can be written as so. So you basically have a vector C, which is for constraints, which is depending on the Q and on time, equal to 0. Okay, please note that this is a vector equaling to another vector. Okay, this is a column vector equaling to a column vector. This is a vector. What is the dimension? Is basically NC times 1, where NC is the number of constraints, right? So of course this is NC. Non-holonomic constraints said are typically, they do actually have this form. They not only depend on this, the state variables Q, but also on Q dot and on T, equaling to 0. We will make example of both. But the most important thing, this is always NC times 1, always NC times 1. But the most important thing about this differentiation than we've done is that they will eventually force us to come out with two different formulations for the equations of motion of our bodies. Because the equations of motion eventually for our bodies will be a way to describe through equations the way that our body can move, okay, as an effect of forces or torques exerted on them, and as an effect of the constraints that will limit their possibility to move in space, okay? And a great part of this treatment will focus on how to include, how to consider in the writing of this equation the constraints, how to embed them, okay, how to include them easily. And in fact, one of the choices, okay, when we're talking about general parameters, okay, generalized parameters, is actually choosing them so that the enforcement of our constraints is as simple as possible, okay? Because otherwise, and this is really the final thoughts, and I leave you with this consideration. Why would I actually need all of this parameterization? Why should I need one set of parameters of general parameters over the others if eventually they are mathematically equivalent. Why? And the answer is this, because with some of them, the enforcement, okay, of the constraints, this is the real deal, is actually very, very much more easy than with others. And this is, for example, one of the ways that justifies formulation that probably you have already seen, and we will see again, which is the Lagrangian formulation, Lagrangian equation of motion. What do we actually introduce Lagrangian parameter? That's exactly for the reason, to be able to easily include constraints into our equations. Okay, that's it for today. I apologize for the inconvenience in the very beginning of the lecture, but my fault. Okay.